we're going to explain a new idea, which is the interfringe distance. The interfringe distance is by definition the distance between the centers of two successive fringes of the same nature. That is to say, it is the distance between the centers of the successive bright fringes of orders 1 and 2, or orders 5 and 6, or orders -1 and -2, or orders -4 and -5. Or it is the distance between the centers of the dark fringes of orders 1 and 2, or 10 and 11, or -4 and -5, and so on. That is to say, if K is the order of a certain bright fringe, then the order of the bright fringe that follows is K plus 1. That is to say that the bright fringe of order K, there exists an abscissa xk, and to K plus 1 there exists an abscissa xk plus 1. If, for example, here's the abscissa xk of the fringe of order K, be it dark or bright, xk plus 1 is the abscissa of the next interference fringe. What is the distance between the centers of these two fringes? It is called the interfringe distance I. Note that this is x plus 1, k plus 1, and this is xk. The expression of I is xk plus 1 minus xk. We know that the abscissa of a bright fringe of order k is xk equals to k lambda d over a. Then the abscissa of the bright fringe of order k plus 1 is xk plus 1, where we replace k by k plus 1, and we get k plus 1 lambda d over a. The interfringe distance, which is the distance between two successive bright or dark fringes, becomes I equals to k plus 1 lambda d over a minus k lambda d over a, which is lambda d over a. Now for dark fringes, we know that the dark fringe of order k has an abscissa xk equals to 2k plus 1 lambda d over 2a. Then to find the abscissa of the dark fringe of order k plus 1, we replace k by k plus 1, and we get 2 into k plus 1 lambda d over 2a. The interfringe distance is xk plus 1 minus xk, which is 2k plus 3 lambda d over 2a minus 2k plus 1 lambda d over 2a. And we also obtain lambda d over a. Even with the experiment, we can verify the interfringe distance is always constant. The distance between two successive fringes of the same nature will always be lambda d over a. Now we're going to verify this expression experimentally. By changing a, which is the distance between the slits, and by changing d, which is the distance between the screen and the plane of the slits. Here we have the interference pattern obtained by Young's setup, where a equals 0.25 millimeters. This pattern is obtained for a equals 0.3 millimeters. And this pattern is obtained for a equals to 0.45 millimeters. When summarizing the experimental results, we notice that I is inversely proportional to A, which is in accordance with the expression of the interfringe distance. Now we're going to bring the observation screen closer to the plane of the slits. Notice how as D decreases, I decreases as well. In this new application, consider Young's setup, where the distance between S1 and S2 is 0.15 millimeters. The distance between the plane of the slits and the observation screen is 1.8 meters. The source S is on the perpendicular bisector of S1, S2. The wavelength of the light that illuminates the slits is 530 nanometers. Part 1. In the first part, we have to find the interfringe distance I. So how can we calculate it? We use the formula I equals to lambda d over A, which is 530 times 10 exponent minus 9 times 1.8 over 0.15 times 10 exponent minus 3. And the answer is 6.36 times 10 exponent minus 3 meters, or 6.36 millimeters. In part 2, we change D. We count 5 successive bright fringes spread over 4.2 centimeters. In part A of this question, we have to calculate the new interfringe distance. So we count 5 successive bright fringes. This is the first, this is the second, the third, fourth, and the fifth bright fringe. The distance between the successive bright fringes is I. The distance between the outermost centers is 4.2 centimeters. So we have 4I. And 4I is equal to 4.2 centimeters. Then I equals to 4.2 over 4, which is 1.05 centimeters. In part B, deduce the new value of D. We use the formula I equals to lambda d over A. Since we have a different value of I, and consequently D, we're going to call them I1 and D1. Lambda remains constant as well. And as a result, D1 equals to I1 times A over lambda, which is equal to 1.05 times 10 exponent minus 2, converting to meters, times 0.15 times 10 minus 3, converting to millimeters, over lambda, which is 530 times 10 exponent minus 9. And the answer is 2.97 meters, or approximately 3 meters. In part 3, D is equal to 1.8 meters. We change the distance between the slits A such that the distance between the center of the fourth bright fringe and the center of the third dark fringe, taken from opposite sides of the central fringe, is 2.48 centimeters. What does it mean on both sides? Let's go to the figure. When S is equidistant from S1 and S2, the central fringe is at O. We want to find the distance between the center of the fourth bright fringe and the center of the third dark fringe on opposite sides of O. That's to say, if the fourth bright fringe is found in the upper side, the third dark fringe will be found on the lower side. This is the central fringe. This is the first bright fringe, the second, the third, and the fourth. The dark fringe is found between two bright fringes. So this is the dark fringe, the first one. And this is the second dark fringe. And this is the third dark fringe, of course, taken on the opposite side. This is the first dark fringe, second, and the third. In the first part of the question, calculate the new interfringe distance. How can we use the figure here? The distance between the centers of two successive fringes is I. Pay attention that this is half I, which is the distance between a bright and dark fringe. Let's count how many I do we have. 1, 2, 3, 4, 5, 6.5. So 6.5 I equals to 2.48 centimeters. I is equal to 2.48 over 6.5, which is 0.38 centimeters. In part B, deduce the new value of A. Apply the formula. I equals to lambda D over A. We will denote I by I2 and A by A2 because it's a new value for both. Lambda and D are still the same. A2 equals to lambda D over I2. A2 equals to 530 times 10 exponent minus 9 times 1.8 over 0.38 times 10 exponent minus 2, which is equal to 0.25 times 10 exponent minus 3 or 0.25 millimeters.